Hello guys, welcome back to a brand new video. Before I start the video, make sure you check our channel for more videos like these. And yeah, let's begin into the video. Introduction to atomic structure. Atomic structure is the foundation of chemistry, describing the small blocks of matter. At the core of every atom is the molecules containing protons and neutrons, surrounding by a cloud rapidly moving electrons. Understanding the arrangement of behavior of these fundamental particles is crucial for explaining the properties and reactivity of elements and compounds. This introduction will lay the groundwork for exploring more advanced concepts in atomic and molecular structure. Atomic models for Rutherford to Bohr. Rutherford Bohr model. In 1911, Ernest Rutherford proposed a model of the atom with a dense, positively charged nucleus and a lightweight, orbiting electrons. This was significant departure from the previous accepted plum pudding model, where the positive and negative charges are evenly distributed. Bohr's model. In 1913, Niels Bohr built upon Rutherford's work, introducing the concept of discrete energy levels that electrons occupy around the nucleus. This model helped explain the observed emissions spectra of atoms and the stability of certain electron configurations. Modern atomic models. Subsequent developments, such as the quantum mechanical model, have provided an even more accurate and comprehensive understanding of atomic structure, including the wave-particle duality of electrons and the probabilistic nature of their distribution around the nucleus. Electron configuration AUFB principle. Filling electron shells. The AUFB principle describes how electrons fill the available energy or shells in an atom, starting with the lowest energy level and progressively occupying higher levels as more electrons are added. Electron subshells. Within each main energy level, there are smaller sublevels or subshells that electrons can occupy. These subshells are labeled using the letters S, P, D, and F, which correspond to different shapes of the electron's wave function. Building up elements by following the AUFB principle, we can determine the electron configuration of an element from the simple hydrogen atom to the most complex naturally occurring elements. This understanding is crucial for predicting an element's chemical properties and behavior. Valence electrons and periodic trends. Valence electrons are the electrons in the outermost shell of an atom, which are primarily responsible for an element's chemical reactivity and the formation of bonds. Periodic trends. The periodic table is organized in a way that reveals trends in atomic properties, such as atomic radius, electronegativity, and ionization. energy which are closely related to the arrangement and number of valence electrons. Predicting behavior. Understanding the periodic trends and the role of valence electrons allows us to predict the behavior of elements and the type of compounds they are likely to form, which is elements for understanding chemical processes and reactions. Quantum mechanical model of the atom. Wave-particle duality. The quantum mechanical model of the atom describes electrons as having both particle level-like and wave-like properties known as wave-particle duality. This concept helps explain the probabilistic nature of an electron's location and behavior. Quantum numbers. The quantum mechanical model introduces a set of quantum numbers N, I, M, and S that define the specific energy levels, shapes, and orientations of electron orbitals within an atom. Probability distribution. Rather than orbiting the nucleus in well-defined paths, as the Bohr model, electrons in the quantum mechanical model exist as probability distribution, where they are most likely to be found. Computational modeling. Advanced computational methods such as quantum mechanical simulations allow researchers to model atomic and molecular structures and predict their properties with a high degree of accuracy. Electron orbitals and quantum numbers. Orbitals. The s orbitals are spherical in shape and have a single electron that can occupy them. P orbitals have a dumbbell-like shape and can accommodate up to 6 electrons. D orbitals have more complex shape and can hold up to 10 electrons. The f orbitals have even more intricate shape and can accommodate up to 14 electrons. Pauli exclusion principle and Hund's rule. Pauli exclusion principle states that no two electrons in an atom can have the same set of quantum numbers. This principle helps explain the electron configuration of atoms and maximum numbers of electrons in each orbital. Hund's rule suggests that when electrons occupy degenerate orbitals with the same energy, they will occupy them singly with parallel spins before pairing up. This maximizes the multiplicity of the atom and its overall stability. Electron arrangement. The combined application of Pauli exclusion principle and Hund's rule allows us to determine the most stable electron configuration for any atom, which is essential for understanding chemical reactivity and bonding. Exceptions to the electron configuration. While the AU-FAB-AU principle and electronic configuration rules generally hold true, there are some exceptions where the observed electron configurations deviates from the expected arrangement. These exceptions are often driven by the stability of the partially filled D and F subshells, as well as the shielding effect of inner electron shells. Atomic Thank you guys for watching. Make sure you like and subscribe, and make sure you check our channel for more videos like these, and I'll see you guys next time.